Good morning. Push the exam out of the way. I started grading my exams last night, and this class is 4th on the list. Just to give you an idea.
What's what?
4th on the list. Once I start grading, which only doesn't take me long, a day or two, just how long it's going to take me to get to it, so it may take me a week to get to them. But once they're graded, they will be posted on Blackboard, so you know. And as a general rule of thumb, if you ask me when the exams will be graded, it takes me longer. We did finish up with polynomials before the exam, right? So today we look at the rational function. Rational function, any function in the form p of x over q of x, where both p and q are polynomials. And obviously q of x cannot equal 0. Domain, all real numbers except those that make the denominator 0. So all real numbers except for the x where q of x is equal to 0. Written this way. One other piece of terminology that's going to be important is the notion of proper versus improper. We say a rational function is proper if the degree of the numerator is less than the degree of the denominator. Right? Much like a proper fraction, the numerator is smaller than the denominator. If you're given a rational function, you're asked to make it proper and it's not, that's where you do the division that we did. Right, and then write it in the form of your q of x plus r of x over d of x. Again, that will be important in Calc 2. Extending on notation that was introduced with polynomials. Sadly, I had to miss, but that video was posted for you. So this means x is approaching a from the left. This is x approaches a from the right. Right, obviously from the left, x is less than a. From the right, x is greater than a. Notice it's not or equals. Right, these two were introduced already. X is increasing without bound, x is decreasing without bound. Here we have f of x is increasing without bound. F of x is decreasing without bound. And so these also should have been introduced with polynomials. This is going to be new. F of x approaches a. Important to note, again, for these three, never has to actually equal a. Just has to approach it. So the notion of a vertical asymptote, you should be familiar with it from algebra. Vertical line x equals a, where the graph tends towards either positive or negative infinity on one side, on either side. So this is said math. So this is the mathematical statement of it. As x approaches a from the left, f of x tends to plus or minus infinity, or as x approaches a from the right, f of x tends to plus or minus infinity. You'll re-examine this definition. The actual formal definition in calculus has to do with limits. Here's a question for you. Can a graph cross a vertical asymptote?
What?
Can it cross a vertical asymptote? No, it can't. It would violate the definition. Then you wouldn't be going to plus or minus infinity on one side. Can it touch a vertical asymptote? So can you touch a vertical asymptote?
What do you mean, like plot a point with it?
So touch, can it actually hit the asymptote? Never cross it, just hit it.
Yeah.
Yes, it can. And here's an example. Vertical asymptote is 0. X equals 0. Because on one side, specifically from the right, you are going to infinity. Even though from the left, you actually hit the asymptote. The definition doesn't say it has to go to plus minus infinity on both sides. It says or one side or the other or both. Would it be able to touch the asymptote more than one time? No, then it wouldn't even be a function. Horizontal asymptote. Horizontal line, y equals b, where the graph approaches the line as the inputs increase or decrease without bound. And so stated mathematically, as x approaches plus or minus infinity, f of x tends to be Can we cross a horizontal asymptote?
Yeah.
Yes, we can. What's the maximum number of times you could cross the asymptote?
Twice. Twice.
It's not once. It's not twice.
Infinite.
There is no maximum. You could theoretically cross it an infinite number of times.
We're talking about the x-axis, right? That's what it means.
Horizontal line.
So like any horizontal? Okay.
Let's take a look. This case, it's crossing only one once. Right? Now it's crossing multiple times. Horizontal, all we care about is long term. At the end. So what it does in the middle doesn't affect the horizontal asymptote at all. Of course, it's simple to determine if your function is going to cross the horizontal asymptote. Just set the function equal to the value of the asymptote and solve for x. If you get x values, then you know you're crossing. Or touching. I don't know if you cross or touch. If you want to determine if it crosses, just determine the sign on each side of that point. Different signs means it did cross. There are other types of asymptotes as well. Broadly, they are categorized linear. So these would be things like asymptotes that are parabolic or cubic in shape. We are only concerned with one type in this course, and that is the slant or the oblique. That is a linear asymptote. So something like that would be an oblique asymptote. The function tends towards that line as x goes to infinity. Or negative infinity, so I could also have one down here. Something like that. Right, and slant asymptotes will always have the form of a line, y equals mx plus b. For discontinuities, there are several types. You will study them more in depth in Calc 1. Right. Specifically, we only look at one, the removable. The other two would be the jump and the infinite. So removable discontinuity occurs in the graph of a rational function at x equals a if a is a 0 for a factor in both the numerator and the denominator. Right, so you can factor both numerator and denominator and get like x minus a in both of them. Then they would quote unquote cancel, so to speak, and it would be removable. However, multiplicity has to be greater than or equal to in the numerator than the denominator. You can't have a larger multiplicity in the denominator. Otherwise, it's not removable. Right? You have x minus a squared in the numerator, but x minus a to the fourth in the denominator. You're not able to get rid of that 0 in the denominator. So that wouldn't be removable. In the case where the 0 is removable, it's not a vertical asymptote. Right? So x equals a would not be a vertical asymptote in that case. But that doesn't mean that a is in the domain, because it's not. In which case you'd have a hole at the point a, f of a. Vertical asymptotes. When trying to determine the vertical asymptotes of a rational function, generally the easiest thing to do is fully factor both the numerator and the denominator. So how would we factor the numerator? Can't be factored. So it's just x. How would we factor the denominator?
X plus 2x minus
That is a difference of squares. Is there anything you can cancel? No. Now just list out the zeros of the denominator. What are the zeros?
two and negative 2.
So those would be your vertical asymptotes. Remember that vertical asymptotes are lines. You have to write x equals. You can't just write -2. That's a point. You had your hand?
The negative 2 and the 2, that just where it's hitting on the asymptote? Or
They are the asymptote.
oh, that's where it's creating the for vertical, that's where it's creating the line. Okay.
Right. More detailed explanation, you need the concept of limits to understand how, when it's zero in the denominator, it's going to be an asymptote going to plus or minus infinity. That's the notion of a limit. Right. But for rational functions only, vertical asymptotes are when the denominator is 0.
Okay.
How do you factor the numerator? So just 2x. Right? How would you factor the denominator?
X plus 2, X plus 3.
You can't.
You can't. Not in the real plane, you can't. That's how it would factor if you're in the complex plane. But of course we're not. So it just stays as x squared plus 4. So that was already fully factored for us. Nothing to cancel. Zeros of the denominator. Technically has zeros. Plus minus 2i. But actually, we just want the real zeros. There are no real zeros, right? So there's no vertical asymptotes for this function. How do we factor the numerator? It's linear already. What about the denominator?
X minus 2x plus 1.
Is there anything in common? No. So we have vertical asymptotes. Zeros of your denominator. -1 and 2. So your asymptotes, x equals -1, x equals 2. We don't really have to worry about factoring. It's pretty obvious, but we're going to factor anyway, see if we can remember. How's the numerator factor? That one's difficult. That's just 3, right? How's the denominator factor? You think back to algebra.
Can we do x plus 2, x plus 2, x plus 2?
So it wouldn't be that. I do agree there's an x plus 2.
And then would it be x squared minus 2x plus 4?
That is the factor of the sum of cubes. That's the formula for sum difference. Again, it was really obvious there would be nothing in common. Real zeros of the denominator. You don't even need to look at the factored form. X cubed plus 8 equals 0. X cubed would have to be what? So x cubed would have to be what? Right, what plus 8 is 0? 8 plus 8, 16.
Oh, 0.
What plus 8 is 0?
Negative.
-8. X cubed has to be -8, so what's 8? What is x? That quadratic x squared minus 2x plus 4 has no real zeros. Both those zeros would be complex. So you can ignore them. So there's one Virgo asymptote, x equals -2. How'd you factor the numerator?
X minus 1.
How'd you factor the denominator?
X plus 1, x minus 1.
Are there common factors? What's the common factors?
X minus 1.
I think I mentioned this already. Is that a true statement as it's written?
Wouldn't you just have to like put it can't be -1 and then it is?
So as it's written, it's not a true statement, right?
Oh.
Because in order for it to be a true statement, it has to be true for every possible value of x. As you just said, if x is -1, or not -1, if x is 1, that's not true. But it is true for everything except for 1. Now you look at your reduced fraction. What are the zeros of the denominator?
Negative.
X equals -1 is your only vertical asymptote. Notice then plug 1 into that reduced fraction. What do you get?
1 and 2.
Go away, Copilot. That point would be a hole in your graph.
That means the line's discontinuous. Like
It is discontinuous,
Okay.
right? But it would only be discontinuous at that one point. So generally the easiest thing to do is just draw the graph, and then at that point, erase and put a hole. Because otherwise the graph is identical. This is what we mean by removable discontinuity. Because I could just redefine this function. I've now removed the discontinuity at 1. Wherever you have to be careful. Because a lot of graphing software, you just put in the function that you want to find the graph of. What's wrong with that?
There's not a bullet 1 for 1.
It will not plot the hole. It'll treat it as if it's continuous at the hole. Even though I'm pretty sure if I try to go over, it's not even going to show 1. Oh, it did. Oh dear. So it's actually saying that it's 1 comma half, which it's not. It's undefined. So that is an issue. With Mathematica, which is what this is, I can work around that. It's not fun. I have to code in the hole. So I have to actually recognize there's a hole first and then code it in to get the hole in the graph. Also, your calculator is not going to be allowed to do that. You can't code in a hole. So just be advised of that. Because if you just try to look at the graph and go, oh, you know, okay, only -1. This continues that. Continues everywhere else, and that's clearly not right. Technology is only as smart as its user. For now, anyway. When it becomes smarter than the user, that's when you're in trouble. All right, moving on to horizontal asymptotes. So for rational functions, finding horizontal asymptotes is actually really easy. However, I'm not going to use that method because it only works for rational functions. For any other type of function, you can't really do the method. So we'll kind of look at the logical way to do it and see if you can recognize the pattern. So remember what we want for horizontal asymptote, right? We want x to get really, really large or really, really large in the negative direction, right? Oops. So let's just say for x much larger than 0. That's what a double greater than means, much larger. Well, numerator stays the same. And it's going to be 4 times a really large number squared. Take a really large number. Five Googleplex. Googleplex is a 1 with a Google zeros. And a Google's a 1 with 100 zeros. So it's a very large number. Add 4 to that. Is there really much of a difference? No, right? Like you have $100 trillion in your bank account and you deposit $4. Does your bank account even freaking notice it? No. So for an extremely large x, that's really just x squared. That plus 4 doesn't really matter. Yes, the plus 4 is going to make it larger, but not that much larger. Again, for large x. Wasn't that just 4? So that's your asymptote. And that's what we would say mathematically. As x approaches infinity, f of x tends to 4. It will never actually be 4. Right, but it gets really close to it. To the point where you can just treat it as 4 safely. We're talking about like 3 point. Would it be 3 point or would it be 4 point? Be 4 point. Like 4 points, a million zeros and then a 1.
But isn't that 4?
Mm-mm.
No, that's 4.
4 point, a million zeros and 1. Right, so it's a decimal. So it's really close to 4, but it's not actually 4.
Yeah.
But your calculator doesn't have that kind of accuracy. So it would actually give you 4. That's the whole point of what we're saying here.
Okay.
Right, it's going to get to the point where, in terms of accuracy, you can just treat it as 4 safely. Right, it'd be like, I guess the way I could really look at it is, probability of you walking out of your door in the morning and getting struck by a bolt of lightning. You would say it's not going to happen. The probability is not 0, though. It's a very small probability, but you can treat it as 0. Right? That's kind of the best way to look at it. Really fun one would be, what's the probability of you just bursting into flames right now? According to quantum mechanics and stat mech, that probability is not 0. It is possible. Not technically. It's been proven.
But it hasn't happened.
It is possible.
Yeah.
It's just the probability is so small you need to wait around longer than the age of the universe for that to happen. So, effectively 0. That's a fun example. I love those examples. Combustion. Do the same thing for a very large x in the negative. So say for x much less than 0. Again, numerator, not going to change. If you have a number much less than 0 and you square it, it's going to turn positive, right? At which point, now the analysis becomes the same as above. You have a really, really large number and add 4 to it. It doesn't really matter. So the denominator is effectively x squared, which again is 4. So as x tends to minus infinity, f of x tends to 4. 4 is your horizontal asymptote. And again, it's a line, so you have to write it in the form of a line, y equals 4. So for very large x, numerator, nothing's going to happen to that, right? It's a single term, you just get x squared. Denominator, we can use the same analysis as before. You have a very large number, add 4 to it. Effectively, it doesn't change it. So this function for a very large x behaves as x squared over x, which is just x. As x gets very large, x gets very large. So we'd say f of x tends to infinity in this case. Because how are we treating f of x in this case as x for the very large x? Right, so however x behaves, f of x is going to behave. Now for a very large x in the negative direction. So here's a fun little example that may hit really close to home. So we're taking a very large negative number. So let's say you went to med school and racked up $600K in student loans. You make a $4 payment. Did your student loan even notice it? No, it kind of just belched. Right, it's kind of like a rocket ship going into the sun, just kind of, and that's it. So x plus 4 would still behave as x. Well, x squared over x is just x. Right? As x tends to negative infinity, f of x behaves like x. So again, it's going to do the same thing. No horizontal asymptote. I can say this does have a slant asymptote, though. But that's not what we're being asked for right now.
But that's because it's x. So it'd be just constant.
No, slant asymptote
Oh, you mean like, okay.
is a line.
Yeah.
A diagonal line, right? Not
Yeah.
horizontal over, it's an actual diagonal line of the form y equals mx plus b.
Okay.
I do have problems where we're going to find the slant asymptote, so we'll go over how to do that. Right, so for very large x, 2x is just 2x. Take a very large number and square it. It's still very large. So let's go back. You have a $10 billion net worth. You spend $4. Did that really affect your net worth? So subtracting 4 from a very large number really has no effect. So we can treat the denominator as just x squared. And that's just what, 2 over x? As x tends to infinity then, we're treating f as 2 over x. So what happens when you divide 2 by a larger and larger number? It tends to 0, doesn't it? And it keeps getting smaller. 2 over 10, 0.2. 2 over 100, 0.02. 2 over 1,000, 0.002. So on and so forth. We already know 0 is an asymptote then. Question is, do we have a second? For rational functions, you won't. Rational functions, you're only ever going to have one. And again, let's just do the analysis. For x being very small, or very large in the negative direction, again, 2x still stays as 2x. Same analysis, you're taking a negative number, squaring it, it becomes positive. So same thought analysis as for very large x, your denominator is x squared, which is just 2 over x. So now, what we're dividing 2 by is an increasingly larger x, but in the negative direction. Right, so 2 over negative 10. Negative 2 tenths, right? Negative 2 100ths. So it'd be negative 0.2, negative 0.02, negative 0.002. What's happening?
It's moving away from zero.
Is it? Negative 0.2, negative 0.02, negative 0.002. It's again tending towards infinity. Or not infinity, I'm sorry, tending towards 0. Right. So the horizontal asymptote is y equals 0. Oh, and here you can easily see you're actually going to hit 0 at x equals 0. So at the origin you cross or touch. Without looking at it, I don't know. I think it's crossing. It's a multiplicity 1, 0. So it's crossing. So you're across the origin. So you're crossing the horizontal asymptote in this case. What about here? Do we cross 4? Well, to see if we do, set that equal to 4 and solve for x. Which I'm too lazy to do by hand, so. Thank you, technology. You're a wonderful thing. We don't here. There's no solution to that. So for very large x, take an absurdly large number and square it. It's even more absurdly large, right? Then multiply by 3. It's even more absurdly large. So again, I'm going to use, I think in this case I'll just use a Google because it's easier to write. And so Google's 10 to the 100th power squared would be 10 to the 200. So that first term is 3 times 10 to the 200. That's a 3 followed by 200 zeros. Five followed by 100 zeros. If you add that to a 3 followed by 200 zeros, is there a significant difference? You're off by a magnitude of 10 to the 100th. It's not really going to notice it. Add 2, and it's really not going to notice it. So the numerator behaves like just 3x squared. And the denominator, again, 4 followed by 200 zeros, now add 1. There's really not much of a difference. That's kind of like 3 over 4. That means that fx is going to tend to 3/4. For a very small x, so again, x is very large in the negative direction. So instead of 10 to the 100th, you use negative 10 to the 100th. In the numerator, that first term is still 3 times 10 to the 1 to the 200th, right? It's 3 followed by 200 zeros. But now instead of adding the 5 followed by 100, you're subtracting the 5 followed by 100, followed by 100 zeros. Again, is that 3 followed by 200 zeros really going to notice? Not so much. Add 2 back into it, and it's still not really going to notice, right? Numerator still behaves as 3x squared. And denominator is the exact same analysis because you're squaring it. So denominator is still behaving as 4x squared. The function still behaves as 3/4. Horizontal asymptote is the line y equals 3/4. Yeah. Let's just examine it. What was that? I actually want to do is numerical approximation of that. That'll work. Just do like 10, 10 to the 3rd, 10 to the 6th, 10 to the 9th, and 10 to the 12th. Let's see if that's enough. Oops, okay, I had those, I had FX stored. Do it that way, that should be fine. And so just look at a table of some values. And look what's happening as we let x get progressively larger. What's happening to f? Right, becomes 0.75. So that analysis was correct. I could keep going, right? Add in 10 to the 15th, still 0.75. I'm just going to change it now to negatives. What's f doing as x gets larger in the negative direction? 0.75. Right, so again, that analysis was correct. By the way, that's the notion of a limit. Oblique asymptotes. We will only have an oblique asymptote for rational functions if when we perform the division, you get a linear quotient. Again, I'll let you notice the pattern of when that would happen. So let's divide. It's improper, right? So there's going to be a quotient. And oh, look, the divisor is now of the form x minus k. We can use synthetic division. Coefficients of the dividend are what?
One less. One less.
What do you mean by one less?
Like it was x squared equals to x.
I'm not asking for the degrees.
Oh.
I'm asking for the quotients. Or not the coefficients. What are the coefficients? Is that it?
Yeah. Oh, 0.
Is that it?
And 0.
Yep. 1, 0, 0. All right, that's x squared plus 0, x plus 0. 1 times 4 is 4, plus 0 is 4, times 4 is 16, plus 0 is 16. This allows us to write f of x in this form. Here's where things are going to get a little hairier. If we let x go to infinity, unfortunately, f of x actually also tends to infinity, which isn't helpful. But look what happens. No, let me leave that. That just simply tells us that's not leading to a horizontal asymptote. But just single out the remainder portion. As x gets very large, what does that portion do?
that small number.
As x gets very large, what does x plus 4 do?
Keep it bigger.
16 divided by a bigger and bigger number.
Small.
To what?
What is it? Just 0?
Tends to 0. For very large x, that remainder just tends to 0. What that means, for very large x, we can just treat f of x as that line x plus 4. That is your slant asymptote. And the analysis would be exactly the same for x much less than 0. Right, that remainder term still tends to 0, so the function still behaves as the line x plus 4. That is your slant asymptote. So the slant asymptote is the quotient, but only if that quotient is linear. Otherwise, it would no longer be a slant asymptote, it would be a different type of curvilinear asymptote, which we're not interested in because those get really complicated to study. I'm just going to call it slant because that's what I'm used to calling it. It's the same as oblique, just two different ways of saying it. So the slant asymptote is the line y equals x plus 4. So if we kind of examine this now, it's at this portion where you can really start to show off the power of Mathematica. First thing I'm going to do is just plot the function. I'm going to plot two functions. Again, I can't actually see the text on my printout. X squared over x. I'm also going to plot x plus 4. Because that was our quotient, right? X plus 4 was the same asymptote. Let's go, I don't know, minus 5 to 5. That's good. Okay, so that's not a large enough domain to actually see it, so let's minus 500 to 500, and you can see the function's approaching that asymptote. Can I actually reduce that to make it nicer? Let's go down to 50. That makes it a little better to see, right? Notice that we're also crossing the slant asymptote here. So again, you can easily determine if you're crossing the slant asymptote just by setting the function equal to the asymptote, right? So we'd set this part here, the x squared over x plus 4, equal to x plus 4 and solve for x. If you get a solution, you're going to at least touch it. To determine if you're crossing it, then you just determine sign, I say quote unquote, on either side. If one side is greater than, and the other side is less than, in this case, what is that point? Whatever that point is, plug that point into x plus 4. It's going to give you some value. For the sake of argument, let's just say it's 1. If on one side you get greater than 1, on the other side you get less than 1, you know it's crossing. That's what I mean by sign. Is it positive, larger, negative, less? Here you can see it's going to So that's kind of graphically verifying our slant asymptote. Let's numerically verify it. So here I want to do x. I want a value for x squared over x plus 4. And also of the asymptote itself, x plus 4. And again, for increasing values of x. So again, x, or 10, 10 cubed, 10 to the 6, 10 to the 9, 10 to the 12, and 10 to the 15 plus u's. Got a comma. Oh. Table. There we go. Oh, that's a problem. So I'm going to need to do numerical approximations. Worst part about coding is the debugging. Do the values start to agree? That's what it means to be an asymptote. We've now numerically confirmed it as well. And we can do the same thing negatives. And you get the same. So that is a really good way of checking your analysis. So while you don't technically have access to Mathematica, Mercer's not a Wolfram campus, you can access the online version, Wolfram Cloud, by creating a free account. And that free account, the only difference between the free account and the paid account is your cloud storage. Everything else is the same. So you have the full functionality of a paid account for free. There's a problem with it, of course. It is a coding language. So anyone who's familiar with any kind of coding, it takes a while to learn the language and get comfortable with it. Thankfully, there's a documentation center online as well. Used to be a hardcover book, and oh my God. This was back at, I think Wolfram's up to 14.2 now version. When I first started using it, it was version like 5 or 6. And the only documentation you had was the actual book document. The book was like 10,000 pages. I mean, this thing literally was a deadly weapon. Swinging as hard as I can at someone who's probably going to put them into a coma. It's also a great way to work out. Just lift it up, put it down, lift it up. Want to strengthen your back? Just put it in your backpack. Can't fit anything else in there, but oh, how it's come a long way. It also does a lot of statistics now. So I know on the second project, I had to create a scatter plot. I recommended using Excel because it's the easiest. You can also use Wolfram to create a scatter plot. I think your third project also has to do a scatter plot. Can't remember. So oblique asymptote here. Again, just Find the quotient. Let's see what happens. So write this in proper form, because right now it's improper, right? Well, it's the same divisor, so we can still use that's wrong, actually. I should have been a -4, shouldn't have. We made that negative, that negative. This should have been x minus 4. Not x plus 4. Yet somehow the graph still came out right. It's actually kind of worrisome. What did I do wrong? That looks a lot better. With the right asymptote now. I don't need to go out to -50. That just makes it go quicker. Oops. There we go, now it's fixed. 30 points from everyone's exam for no one pointing out that mistake. So it's still x plus 4, -4 is what we're going to use. What are the coefficients for the dividend? One, zero, zero. Is that it? One more? Yes. 1, 0, 0, 0. Right? It's x cubed plus 0x squared plus 0x plus 0. 1, -4, -4, 16, 16. 4 times 16, -64. Which means we can write f of x squared minus 4x plus 16 minus 64 over x plus 4. Is the quotient linear? No, it's quadratic. Quotient is x squared minus 4x plus 16, right? No slant asymptote. Oh, bummer. The value was not right for me. That's a shame. So we have to do long division. What is the first term we have to multiply by?
2. No, x.
That would give 2x squared. So remember how long division works? Uh-oh. Just had a test on that too. I think there was a division problem in there too, wasn't there? What are you multiplying 2x by to get x squared? And so I agree there's an x, but what do you have to multiply 2 by to get 1? Yep. So you have to multiply half x. Negative 5 plus 5 halves. Should be negative 5 halves, right? Now what are we multiplying by? I'll do the hard part for you. It's going to be negative. So 2 times what is 5 halves?
2.5 over 2.
Okay, I'll buy that. Which is what?
That's 5 over 40.
What is it?
That would be 5 over 40.
Yep. So you multiply by 5 quarters. Or negative 5 quarters in this case, right? Five times 5 quarters. They drop out. What is 3 minus 25 quarters? It's making us work with fractions. How dare he?
Negative 13 over 40.
Yep, negative 13 quarters. This would be our f of x, but I don't like that compound fraction. So I'll just rewrite it. It's not required. Just the compound fractions look hideous. Right? They're very unattractive. Math is 90% aesthetics. Well, again, using same analysis, our quotient is linear, right? So as x gets very large, that remainder term tends to 0. So f of x will behave as the quotient for very large x. That is your slant asymptote. Oh, by the way, I could rewrite that to get rid of fractions. Could write it that way. Or I could write it as 2x minus 4y equals 5. That would be general form of the line, I believe it's called. So oblique asymptote here. And notice I'm not writing the missing terms this time, like I did with dividing in that section. What do we multiply x squared by to get 2x cubed?
2.
Right, 2x cubed dropped out, we get a negative 4x squared minus 3x left. Now what are we multiplying by? They drop out. Negative 3 plus 8. It's just 5x, right? And then plus 4. This is f of x in proper form. Is the quotient linear? That would be the oblique. But let's just examine. Because unlike the previous examples, our remainder here wasn't constant. So does 5x plus 4 over x squared plus 2x plus 1 tend to 0? Do the same analysis that we were doing before. 5x plus 4. You take a really large number, multiply it by 5. Now add 4 to it. Is there really much of a difference? Denominator. A really large number squared. Now 2 times that same number. Add them together. The square dominates, right? So it doesn't really notice the plus 2 times the number. Add 1. Not really going to notice. So that's going to behave as 5 over x, right? And as x gets large, what does 5 over x tend to do? Tends to 0. So yes, that remainder term, the entire remainder term, will tend to 0, which is what we expected. Our slant asymptote here is the line y equals 2x minus 4.
On a test, are we supposed to write down what it tends to? Like how it goes down to infinity, then with that, that's just we're explaining.
Now, if you actually put that work down as explanation, you're more likely to get partial credit.
Okay. Oh, because you broke it down.
Right, so generally speaking, in math, it's the reasoning that matters more than the answer. It's not true in science. Right? Your answer definitely matters more than your reasoning. But in math, we care more about the reasoning. Like, did you understand the process versus making an arithmetic error? Understanding the process is going to be worth more. Right? So if you make an arithmetic error, you don't lose as much as not understanding the process itself. So if you're not confident, you want to explain your answer. This process, by the way, of doing the division and your quotient being the oblique asymptote, would also work for horizontal asymptotes. Take the quotient. If you get a constant, or find the quotient. If your quotient is a constant, it's a horizontal asymptote. So in this case, if you actually do this out, you should already be able to see that's already proper form, right? Your quotient's 0, right? It's already proper. What was the horizontal asymptote? 0, the quotient. Find this quotient. I promise you, you'll get 3/4. That's the quotient. And then the remainder term will go to 0 as you let x get very large. So you could also do division for horizontals as well. And if you get a constant quotient, that would be your horizontal asymptote. For the exact same reasoning as we were discussing for the slant. Your remainder term will tend to 0 as x gets very large in either direction. Then your f of x obviously just acts as the quotient. I don't spend any time in class on finding the intercepts. Right? You should be able to do that very easily. X equals 0, plug it in, evaluate, that gives you your y-intercept. Solve for 0. Right? Set the function equal to 0, solve for x, that gives you the x-intercepts. That should be very easy to do. At this point, we've already done it, so I'm not spending any time on that. I want to spend time on the new stuff, the asymptote stuff. And I'm not a big fan of sketching graphs either. So I don't spend a lot of time in class on sketching graphs, because there's technology for that. But I think your homework will have you sketching graphs. And by sketch, it's essentially just multiple choice. It gives you the graph, it says which one is. It's a sketch graph, and then it says, here are the choices of them. So try and do that on your own. Any questions on the asymptotes? There's one topic left in this unit, and that's modeling with variation. So that we do on Monday. Then Wednesday we start what's in my opinion the easiest unit, exponential and logarithmic functions. Is such an easy topic. In fact, I think it only takes 2 weeks. Yeah, 2 weeks. Yeah, maybe 2.5. About how much modeling I want to do. So homework on this stuff is due next Wednesday, as is the second project. Due next Wednesday. Look at that. We're already going into March. Hard to believe, isn't it? It's already been a month. Actually, it's been more than that. It's been 5 weeks. We got our first exam. It is crazy, isn't it? Which means spring break is only a couple weeks away. And I have a fun assignment for spring break. It's not a hard one. It's actually pretty fun. Using generative AI. So kind of building on the discussion assignment. So it is interesting. It's not hard. We should be able to get it done in a day. What's today? Wednesday? Yeah, Wednesday. Have a great weekend. See you on Monday.